Section 8.5 covers exponential functions. It starts on page 350 in your textbook. So, to get started, first thing we're looking at is a review of how to graph a couple of simple equations. So first we have y equals 2x. Remember, if we have 2x, that's like saying we have a positive 0 or plus 0, so that'll be a 0 y-intercept. So it's crossing right through the center there with a slope of 2 over 1. And then the second one, this is a power function. We looked at these in section 8.4 specifically, and they look kind of like big old U. So, the other thing we need to know how to do for this lesson is to evaluate powers. First things first, 2 to the third would look like 2 times 2 times 2, which would be 8. 2 to the negative fourth, remember that's the same thing as 1 over 2 to the fourth. And when we take 2 to the fourth power, we'll get 1 over 16. And then, of course, anytime we have anything multiplied by, or taken to the 0 power, that's like saying 1, so 3 times 1 is 3. So an exponential function is a function of the form f of x equals ab to the xth power, where b is greater than 0 and b cannot be 1. So example 1, we're just creating a pair of tables for our ordered pairs for either a, which is y equals 2 to the x, or b, which is y equals 1/2 to the x, and then we'll graph those lines. So for the first one, y equals 2 to the x, well, we would just choose our x values. They have -3, -2, 1, 0, 1, 2, and 3. And then we just say, well, what is 2 to the negative third power? We'll do the first couple together. So if our x value is 2, first one we were doing was -3, wasn't it? 2 to the negative third would be the same thing as saying y over 2 to the third, which would be, 1 over 2 to the third, which would be 1 to the 8th. So that's our first value. Then if we do our -2, it's like saying 1 over 2 to the second power, which is going to be y, or 1 over 4 for our y value. -1 is the same thing as 1 over 2 to the first power, which is just 1/2. 0 would be 2 to the 0 power, which would just be 1. And then for our 1 would be 2 to the first power, which is 2. And for 2, we would have 2 to the second power, which would be 4. And for 3, 2 to the third power is 8. So this in the middle here is just kind of where I was working my 2 to the x power out. So these are our ordered pairs. The second one we had was y equals 1/2 to the x power. So they also use -3, -2, -1, 0, 1, 2, and 3. So we'll just do the first one together. So we have x and y. If we're saying our x is the negative third, saying 1/2 to the negative third. So we're going to have to flip this around because of the negative exponent. So this is like saying 2 to the first to the third power, and 2 to the third power is 8, and 1 to the third power is still 1, so that just equals 8, which is where this 8 comes from. Likewise with -2, -1, 0, 1, 2, and 3. And then when we graph these, they should look like this, and those are on the bottom of your page on 350. So you will notice when these are moving along here, they drop down and they get close to the x line, but this is one where we could keep zooming in closer and closer and closer, and we would see that each time it moves over another spot, it's getting closer to x, but it is never actually going to touch x. And same thing over on this side. It gets closer and closer and closer to x, but it's never actually going to touch the x-axis. This is called an asymptote. So an asymptote is a line that a graph approaches but never intersects. So here, in this case, we have a horizontal asymptote because we are never going to actually touch our x-axis. We're just going to get closer and closer and closer. I think I went backwards. There we go. So in both functions, the domain is the set of all real numbers because we are going as far to the left and as far to the right as we can, which will go on forever and ever and ever. But the range is never going to get all the way down to the x-axis. So in example 2, it says graph y equals 3 times 2 to the x power on the same coordinate plane as y equals 2 to the x. Well, y equals 2 to the x is what we did first in example 1a. So in this example, we see that the curve of y equals a times 2 to the x power differs from y equals 2 to the x power. In that, for every value of x, the corresponding value of y will be a times its previous value. Because think of order of operations, we do our exponent first, and then we'll multiply it by that a value. In this case, our a value is 3. So this time, instead of having a y-intercept at 1, we have 1 times 3, so our y-intercept will be at 3, or our a value. So here with our a value, we're saying whatever we're multiplying it by, which is 3 in this case, is going to be our new intercept. Before, we were multiplying it by an imaginary 1, so before our y-intercept was at 1. And you can take a look there at the example on page 351. They don't give it to us here in the slides, but they just took another set of ordered pairs. They show you that the first line in black there is the one that we graphed on the previous page. And then the new red line is the one where we are intercepting at 3. And you can see it kind of becomes more steep. It goes up a little faster. So example 3. Photocopiers and graphics programs allow the user to enlarge or reduce an image using a percentage of the original, which is p. The equation y equals p to the x value can be used to find the effect of successive enlargements or reductions. What percent of the original is the image produced by each of the following? Round to the nearest tenth of a percent. So the first one says 3 consecutive reductions of 75%. Well, first off, our percentage that we're using to reduce it is 75%. So we'll substitute that in for our p-value. So here we'll put in 0.75, and then that gives us y equals 0.75 to the x power right here. And the first one says we are doing this 3 times, so 3 becomes our x value. So we take y equals 0.75 to the third power. We can punch that in our calculator. We're going to round it off, and we are going to get approximately 0.422. Or it is about 42.2% of the size of the original. And then example 3b says, what if we do 4 consecutive enlargements of 150%? Well, once again, we'll substitute in our 150%, or 1.5. So we get y equals 1.5 to the x power, and our x is going to be 4, remember, because we are doing this 4 times. So we have y equals 1.5 to the 4th power. When we punch that in our calculator, we get 5.063, which means that the new image is going to be about 506.3% of the original size. Last but not least, we're talking about compound interest. So up to this point, we've just been working with simple interest, but most real-world investments involve compound interest. And compound interest can be modeled with an exponential function. So simple interest is where there is a one-time payment of interest at the end of the investing period. Most investments, however, involve this compound interest, where interest is regularly credited to the account so that it can begin earning interest along with the principal. So example 4 says the total amount of a $10,000 investment account earning 5% annual interest compounded yearly can be modeled by the equation y equals 10,000 times 1.05 to the nth power, where n is the number of years the amount is invested. Assuming there are no withdrawals from the account, find the balance after the following number of years. So if the total amount was $10,000, that 1.05, remember that's 105%. We're saying we have to multiply this 10,000 times 100% first to say how much, to keep that $10,000. And then we're also doing 5%. So we're multiplying it times 100% plus that 5%, which is the 1.05. And then we said n is the number of years. So the first one is just after 1 year. So n equals 1. So we just take our equation, substitute in 1. Well, 1.05 times 1 to the first power times our 10,000 is just going to be $10,500. So we've earned 5% this year, or $500. What about after 2 years? Well, we'll take it at 2 for our n, punch it in our calculator. Remember, we do our exponents first, so take 1.05 to the second power first, and then multiply it by 10,000, we'll get $11,025. After 50 years, we'll take n to the 50th power, so 1.05 to the 50th power times 10,000 is going to be approximately $114,674 in interest alone. So that's how you can see how these really good investment accounts, like your retirement type accounts, start to really pick up money, and that's how you're able to retire. So hopefully, take good notes on this so that you can retire young. So that's actually it for this lesson. Let me know if you have any questions. I know it was a shorter one. There wasn't quite as much in it. Most of it just deals with input-output type charts and then graphing. Now, I will let you know you are graphing some fractions, so you're not going to have really, really precise graphs. Just try to guess as well as you can on where your points belong. Anyways, that's it. Let me know if you have any questions. Check out your assignment. Thanks.